Okay, I've started the recording, so Riley, whenever you want me to take it over, go for it.
Great, thanks so much, Jan. All right, welcome everyone. Good morning, happy Friday. Welcome to today's webinar. My name is Riley Gutowski and I'm the Member Relations Coordinator here at the Ontario Water Power Association. Thank you so much for taking the time to join us here today. Before I introduce today's presenters, I just want to go over a few housekeeping items with you all. Firstly, this webinar is being recorded and we will share the recording on our weekly member newsletter, Power Weekly, so that next week. We will be taking questions after the presentation, so we please ask that you hold any questions till the end. When our wonderful presenters are done, you can ask your question in the chat, or you can raise your hand and ask your question directly. Finally, in the chat, you will find a link to our webinar survey. It just takes a couple minutes to fill out, and it's really wonderful for us to have the feedback. So we appreciate if you took a moment to fill that out after today's presentation. So the link has just been shared in the chat. I do encourage you to launch that link, open it in a browser, just so when this meeting closes, you do have it ready to go. All right, so on to introductions. So today's webinar is presented by Millstream Engineering and Thordon Bearings on upgrading leaky shaft seals and worn out bearings. So presenting today, we have Greg Ogder, President of Millstream Engineering. Greg is an accomplished mechanical engineer with extensive experience delivering bearing and shaft sealing solutions to OEM and end user customers in the hydropower equipment market. And Ryan Edmonds, Business Development Manager at Thordon Bearings. Ryan has many years of experience solving journal bearing problems in rotating equipment in the hydropower industry. All right, Greg and Ryan, I'm going to turn it over to you, and Greg will start our presentation.
Perfect. Thanks, Riley. Welcome everybody, and thanks for joining us today. Anybody that's been a long-time OWA member may have seen Ryan and I present before, and it's been a couple of years, I think, since our last one, so we thought it would be worthwhile to sort of update everybody on what we've been working on with shaft seals and guide bearings. And so we're going to go through just a quick introduction of Thordon Bearings and then also Millstream Engineering, and then we'll get into talking specifically about shaft seals and guide bearings. So I will jump to the next slide here, and I'll let Ryan tell you all about Thordon.
Well, hello. Thank you, Greg. I'm Ryan. I'm with Thordon Bearings, so business development for our hydropower side. So we are a Canadian manufacturer. Also, we're Ontario manufacturer. So based in Burlington, Ontario, where our production facility, our largest production facility, is there. We have just recently acquired a second facility that's directly across the street as well for an expansion, and there's an additional plant in Poland as well. So anyway, so we're supported through distributors all over the world. So I think we're at 92 or 93 distributors, and we're in over 100 countries. And Greg, who used to be a Thordon guy himself, is now Millstream Engineering, and he is the local representative. So I think he talks about that a little later. So we'll leave that for him. We're manufacturing all the materials in Burlington, Ontario. So that's the elastomer and the Wikigate material. So these are all self-lubricated or water lubricated things that we're making. So it's a great combination of properties that make the specific materials we supply good for the applications. So I think we'll talk a little bit more about that later. But we can go on from there, Greg. Unless there's something you want to add, of course. You're muted, Greg.
Was this my first time or something?
Yeah, first time.
Sorry.
First time.
Anyway, so Millstream Engineering, we're the authorized reps for Thordon Bearings in Ontario and Western Canada. And so anybody that might have seen me in my previous career life, I was working as an employee at Thordon. And then about 3 years ago, we split off and we set up Millstream Engineering as an independent company. And so our focus still is very much centered around Thordon Bearings and for hydropower and industrial customers. So we do a lot of kind of, bearing and sealing related troubleshooting and trying to come up with solutions for people. We also represent a couple of other product lines. We represent a line of industrial valves called pair valves. And also we work with a bronze foundry called the NEA Foundries for different bronze components. But the topic today is all about Thordon and shaft seals and guide bearings. And so with that, I think we'll just get into it.
Greg, you've muted yourself again somehow. It is his first time,
Super
obviously. Yeah.
Super strange. Yeah, sorry. Anyway, we're talking about radial shaft seals today, as opposed to axial seals, and mostly where we've retrofitted seals with Thordon SXL material. So I'm going to go through just a couple short slides just to kind of get everybody up to speed what radial shaft seals look like and how they work. So the idea with the radial shaft seal is that you're sealing on the diameter of the shaft, could be in a vertical or horizontal unit. And the seal itself is built of a series of segments. So you have a whole ring of interlocking segments. And you could have 2 or 3 rings of those segments, like you can see in the picture in the yellow here. And each ring of segments is basically acting to drop the pressure that's being sealed. So by the time you get to the top of the seal, hopefully you've sealed most of the pressure within the turbine. You still have some water leakage through, which is helping to cool and lubricate the seal faces. But you're really just trying to control the leakage to a manageable level as low as you can, but achieving zero leakage is not really the intent of this type of seal. So these seals have been around for a long time. They've been built with many different types of face materials, phenolic laminate, carbon graphite, and different types of polymers. And so Thordon SXL, of course, is the focus of our presentation. But the idea is that these segments are typically machined out of the material that you're using in different shapes, depending on the design of the seal. There's usually some kind of garter springs that are holding everything tight to the shaft. And then you've got some kind of backing plate and anti-rotation pins so that the segments don't spin with the shaft. And usually there's a water feed coming into the shaft seal assembly, which will be some kind of clean or conditioned water, trying to take out the biggest, worst abrasive material. So one of the big advantages using the Thordon material in these seals, for anybody that's ever worked with carbon graphite segments, if you accidentally drop it on the floor, it's very easily chipped or cracked or damaged. And sometimes when you're trying to stretch the spring around the whole assembly, if something lets go, you have an unexpected, some of the parts slip or something, you can easily crack and chip those carbon pieces. And so the Thordon material, for anybody that's held it in their hand, is really tough and it has high elasticity, but it basically, you can kick it across the room and you'll never break it. So that's one of the big advantages. That also comes into play in terms of abrasive resistance when the water supply to the seal is not as clean as we might like it to be. So that kind of brings us to this slide. This is just showing some testing that's been done for abrasive wear testing of different types of materials against basically a rotating shaft with a abrasive slurry material, and measuring how much material is lost over a certain fixed period of time, and then comparing different materials. And so the main materials that we see as seal faces that we would replace in radial seals would really be the carbon graphite or different types of phenolic laminates, which are a fabric and resin composite. There's all different brands of phenolic laminates, and then the Thordon SXL, as you can see, has a much higher resistance to abrasive wearing in this application. So some common sealing problems that we see that come up quite often when we're talking to customers about radial shaft seals. For one, high leakage rates. If you have lots of water coming out of your shaft seal, that can cause problems if you can't get the water away quickly enough. Depending on the turbine, sometimes that's just going straight to a gravity drain, but other times it's going into a sump, which has to then be pumped out. If you can't pump it out as fast as it's coming in, the water level starts to get higher and higher. And eventually that can cause flooding on the head cover. It can cause backing up into an oil bearing. If you have an oil and babbitt bearing above the shaft seal, depending on the design, Kaplan's and Francis and new and old turbines, they're all different geometries that we have to consider. But you can definitely have a case where your leaky shaft seal is now causing your oil and babbitt bearing to be full of water, and then you end up with a wiped babbitt guide bearing, which is kind of the worst case scenario, but it's really the problem of the shaft seal leaking too much. You also can have the problem where if you have too much leakage on the head cover and you have greased wicket gate bearings, you're also washing all that grease into your sump, and now you're pumping greasy water into the river. So you have to have an oil water separator, some mechanism of separating the grease from all of that leakage water. So if you can reduce the total leakage, then that helps all of those problems. So trying to get leakage down to a manageable level is always one of our objectives. The other big problem is that the seals just wear out too quickly. So if the faces are wearing too quickly, depending on the design again of the turbine, this can be a fairly major maintenance intervention to go in and replace all your seal faces. It could take quite a bit of downtime to access it. If it's buried well below a turbine guide bearing, you have to take a lot of things apart just to get down into the space where the shaft seal is. And so that can cause major outages and downtime. So you certainly don't want to be replacing your seal faces every 6 months. Ideally, you'd like to be replacing them a lot less frequently than that. And so then, of course, even worse than long outages are unplanned outages. And so trying to have that really consistent and predictable wear life helps to get scheduling of your repair and rehabilitation a little bit more under control. So before I move on, I'm just going to see if Ryan has any words of wisdom to add to this little section of our presentation.
Oh, I think you're doing a fantastic job there. Yeah, I think you're underselling the fragility of the carbon graphite. But anyway, that's another matter.
Yeah, there's actually a video we have, I think, on YouTube, which we didn't link from this presentation, but it's on Thordon's YouTube channel, I think, where actually one of our Thordon sales guys takes a carbon segment and drops it on the floor to see what happens. So we can share that link later with the slide deck. Anyway, so we're just going to jump to the first poll question, make sure everybody's still paying attention before we get into case studies. So the question is, have you ever experienced problems with leaky shaft seals? Your choices are frequently, occasionally, or never. And we'll give everybody a minute to answer the poll and we will see what we see. If anybody's answering never, it's probably because they don't have a turbine with a shaft seal.
Or occasionally is probably the definition of frequently as well, is my expectation on that.
Yeah, could be.
Yeah, so I think we had 75% say occasionally, 25% say frequently.
All right, perfect.
Never.
Yeah,
No
so
nevers.
certainly, yeah, this is, I mean, it was, we kind of expected the answer based on, conversations we've had with many customers over the years. It's not every turbine that has a problem with the shaft seal, but it definitely comes up, and sometimes people don't realize it's a problem. They've just become accustomed to replacing the seal faces more frequently than we think maybe they should. So anyway, we're just going to go through a few examples.
There's also the case of the turbine design as well, where some turbines are somewhat in a state of vacuum. So if their seal's not functioning properly, they might not know until they change something about it. So if base load units continue to run, because we've also had people say that, no, I haven't changed that thing in 10 years. And then they go shut the unit down and realize that it's not even there. So that stuff happens too.
Yeah.
Sorry.
No, it's okay. So first example, basically, I'm just going to go through slides of different examples. These are all things that we've worked on in the last few years. And so this first one is with Ontario Power Generation at the Chenot station, which is on the Ottawa River, for anyone who doesn't know, built around 1950. So there's 8 vertical propeller turbines in that station, 15 megawatts each, and not a very high head. It's about 40 feet of head. The shaft size is 27 inches, spinning at 95 RPM. And the water pressure that we have to seal under that seal is about 18 PSI. So it's not a crazy high pressure. And the original shaft seals were using carbon segments for quite a few years. But as we got talking with them about trying to improve the wear life and also get the leakage reduced a little bit, we ended up supplying the first set of Thordon seals in early last year, summertime last year, I guess. So this one, we did a couple of things. We used the Thordon SXL elastomer to make the seal segments in the same shape and size as the carbon graphite components. So we could directly retrofit them into the existing housing. One of the challenges here, and one of the reasons they wanted to try to get longer life out of the segments, you can see that nice small dark hole there is where somebody has to crawl down to try to replace those seal segments. And so the longer we can get between replacements, obviously, the nicer that is for the maintenance staff at the plant. We also, in this case, supplied small water filtration skids to get a cleaner water supply to the seals. So the original setup was just taking water from the main cooling water header, which really just had a pretty coarse level of filtration. And so we took that water and then put it through a cyclone separator supplied by Thordon. This is the Thordon water quality package. And that's bringing our filtration level down to be less than 100 micron particle size. And it also ties in a flow alarm, so we know that we're always getting a minimum flow and pressure required to the shaft seal. So we did the first unit in the summertime. We did the second one late last year, and we've just now, earlier in 2024, supplied the seals and water filtrations for working on changing the other 6 units at the station. So through the rest of this year, we should see all of those turbines switched over to the Thordon material. This one's a little bit smaller. We'll move out to the west coast. So this is with Intergex in BC. It's the Walden North generating station. So at this site, they have 6 horizontal Francis turbines, about 3 megawatts each, significantly higher head here. We've got 42 meters of head, and it's at 295 millimeter shaft size. So quite a bit smaller shaft, but still using the same idea with the segmented seal. We have about 60 PSI under the seal in this location. And the original design here was using the phenolic laminate segments as the sealing faces. So the pictures here you can see on the right, that's the previous phenolic laminate segments. And so we supplied a set of Thordon SXL segments along with new compression springs, new garter springs. We supplied them into the first turbine at that station in 2021, which has been running quite well since then. You can see the drawing here. I've turned it on its side because it's a horizontal unit, but there's where the seal segments are, and then compression springs and garter springs. And so we're just in the process now of supplying segments and springs for the other 5 units at the station. So those should all be retrofitted as well in the next 12 to 16 months or so, depending on how much they dive into all of their units. But they're going to work on upgrading all of them over the coming year. What's next? So the next one, back to Ontario. This is with Peterborough Utilities. So this is at the London Street station. And so this one is a Voith turbine. There's S-type Kaplans, about 3 megawatts each. So we actually have 2 seals on this shaft. There's an upstream and a downstream seal. One's on a 350 millimeter shaft, one's on a 500 millimeter shaft. These were also originally using carbon segments. So we supplied Thordon SXL for this station last year. And in this case, the motivation really was they pretty urgently needed replacements. So they were working on an outage, realized that they needed to replace the carbon segments and didn't have sufficient parts in stock as spares. And so we got the call, hey, can you make something that would be able to retrofit this quickly? And so we luckily were able to get rough material from the factory in Burlington, get it to this machine shop straight away, quickly, design and model up the shape to replace the carbon pieces. And we were able to deliver that, those new segments to the customer within 2 weeks, which we felt was pretty good accomplishment, especially in the month leading up to Christmas when everything kind of gets a little hairy trying to get things done by the end of the year. So we supplied that for the first units at the end of last year, and then we supplied some more spares in the beginning of this year. As far as I know, everything there is also running well.
You might note on the first Chinook one as well, we also supplied that in 2 weeks on an emergency also to start that process of doing all the units in that station.
Yeah,
It's
that's
com-
true. Yeah, that's
Yeah.
and that's one of the big advantages for us with Thordon having the factory right in Ontario is the rough material, the Thordon SXL is made basically every week. It's produced in the factory. And so we can get the starting material from the factory very quickly. And then it's just a matter of scheduling with the machine shop. And depending on, other work that's going on, we try to find a machine shop, one of the partner shops that we work with, and get the work done as quickly as we can when we have those rush orders coming through. So this one, I'll jump back to the West Coast again, and then I'll hand it to Ryan for a couple examples. So this one is Dask Creek. This is with Blue Earth Renewables, also a Voith turbine originally, horizontal unit. Same thing, originally fitted with carbon segments. This was the carbon pieces. And this also was a rush order that we just shipped in early March. So these ones literally left the shop last week and should be installed quite soon. So I will hand it to Ryan to talk about a couple more big ones, and then we'll move on to turbine guide bearings. Oh, Ryan, now you're muted.
Oh, my first time too. Sorry. So this is the Manic 5 generating station, which is one of Hydro-Quebec's larger stations and probably one of the prettiest stations as well, if you ever get a chance to look at it. Looks very nice. So yeah, there are 8 units in this facility. So there are 200 megawatts. There's 2 power stations on site here as well. So these were carbon graphite seals when they originally started. So this is a picture, I guess in the center there, you can see the original carbon segments. Thordon was able to model our segments to replace. But one of the other things that we can do with the Thordon material that I don't think Greg's touched on yet is because of the fragility of the carbon graphite, which is it's very similar to pencil lead. So if you want to do a home example for yourself, sharpen a pencil for a very long time and then see how easy the material will break off. But because of that fragility, there's things that we don't we can add to our seal segments, like a radial groove on the inside diameter that allows water to the center of the seal segment that provides a hydrodynamic lift of the segment to help it last a long time. But we can also make the segments longer. So in this case here, we cut the segment count in half, which each segment provides a leak path. So in this case here, we've cut the leak paths in half over the existing carbon. So these seals were originally purchased in 2019. And as Greg mentioned, even on these large units, accessing a seal is very difficult. And due to COVID, these seals couldn't be changed for a long time because it's a confined space and you require more than one person in that space. So it was a proximity thing that dragged this out for a long time, but they did install in 2022. And I'm not sure if I'm correct on the 3 seals in 2023, but they are going down the path of doing the remaining units. There's definitely 2, and I think it's 3, but I could be wrong. So if anyone's on here that's from there, I apologize for the error. But again, it's a success, but it goes in line with what we've seen with every seal installation we've ever done. It's the fact that it works better. It's easier to install and it leaks less, and they find out it lasts many, many times longer. And then we do the rest of the station. So I think we went the wrong way. And then the next one we're going to talk about is limestone generating station. So these are this is Manitoba Hydro's largest station. It's relatively new by Canadian standards, I would say. So in the 90s, and there are 134 megawatt units in the station. So they're 91 foot of head. The shaft diameter is 1,250 millimeters or 49 inches. And these are propeller units. They're only sealing about 30 psi. So we did carbon segment replacement on unit 1, the first unit in 2022, I want to say. So what they were experiencing in this station, and this is why I say when we did that poll at the beginning, when people say frequently or not so frequently, this is one of those examples I often reference, because when we talked to these people originally, it's like, no, there's no seal problem. We just change them every year. And to us, that's kind of a problem. You shouldn't be changing them that frequently. And that's why I always like to or make that comparison or make that comment that define what's good and what's bad. So this one was installed, and Greg and I actually went to site for the installation there. You can see the picture on the right. It's confined space, so we've stuck a camera down in a hole we weren't allowed to go into because we were not qualified in that state. But again, we cut the segment count in half. So they had 12 rings of carbon per, or maybe it was 6, it could be 16. No, it was 12, sorry. So there's 36 pieces, and we cut it to 18 pieces. So what they saw in this unit when it was installed is the carbon seals were leaking about 10, or consuming about 10 gallons a minute to keep the pressure. When we put our SXL into the first unit, it uses between 4.5 and 5 gallons a minute, and it actually seals better. So that's why they see reduced leakage and longer life. We've only been in there for a couple of years now, but that's already longer than the carbon graphite lasts for them. So and they're also going through the process of trying to do the remaining units, but there was some complications in that process, so it's been delayed.
We'll say money complications, not technical complications.
Yeah, it's more like government change things, but anyway, we won't get into that.
Yeah.
Okay. All right.
Yeah, that's great. Ryan makes a good point about the segment count, and so that really is the first step of any shaft seal that we look at. We try to figure out if there's ways that we can improve the design, either improve the segment geometry, reduce the number of segments by making the segments longer and reducing those leak paths between them. Or in some cases, we have to retrofit some other components within the housing as well. If there's some plates or spacers which are worn out, we may replace those as well. So really, we're trying to look initially at, how can we retrofit this seal? We want to try to reuse the big expensive housing pieces as much as we can, and we're trying to stay away from having to put in complete new seal assemblies, because that's usually the big driver of the cost, is if you have to make complete new fabricated steel housing plates. But if we can retrofit everything inside of it and get a better performance from the seal, then that's a great outcome for the customer. And so that's really the first step every time, is just look through the drawings and figure out what's happening and where can we try to make some of those improvements. So sometimes we have to just do a direct like for like swap if it's a really tight timeline, or we don't have the project budget to retrofit other components, but we can at least replace the carbon pieces with the Thordon and still get an improvement in wear life. So each project we try to look at with an open mind and try to improve as much as we can within the constraints of budget and timing. So we're going to move on to the second section here of the presentation, which is focused on turbine guide bearings. Same idea. We'll go through a bit of technical content, and then we'll go through some examples of installations, and then we'll have time for questions at the end on both topics. So the general idea here, as with the shaft seals, is that we're trying to improve the performance and the wear life of water lubricated turbine guide bearings. And so just again, a refresher on what does a turbine guide bearing do for anybody that's a little rusty. So the idea is that the turbine guide bearing, being the bottom bearing or the main guide bearing, or in a horizontal one, it's the one closest to the runner. So this is the bearing that holds everything kind of steady. Usually you'll have other bearings which are supporting the generator. You've got a thrust bearing often, which is in a vertical unit holding the whole weight of the machine. Those are 99% of the time oil and Babbitt bearings. But the turbine guide bearing, which is the one next to the runner, in some cases will be oil and Babbitt, but in other cases will be water lubricated. And so, of course, as suppliers of water lubricated bearings, that's our specialty, and that's what we're focusing on today. From a bearing or bushing design point of view, we would consider this a high-speed, low-load application. So your shaft is rotating continuously at a relatively high speed, but you don't have huge high loads compared to something like a wicket gate bushing, for example, which would be very low speed, but a much higher radial load on the bearings. So when we have a high-speed shaft like this, we have to provide cooling for the bearing so that heat isn't causing damage to the bearing. One of the main reasons to have that bearing as close to the runner as possible is because you're trying to stabilize the shaft and you're trying to balance the hydraulic forces on the runner and keep everything centered and running smoothly. And you're doing that with the capability of the bearing material, but also the water film, which is being developed in it. Similar to a hydrodynamic oil bearing, the film is much thinner in a hydrodynamic water bearing, but we're still using that thin film creation to try to support and carry the load that's being applied. When we talk about heat balancing, what we're really trying to do is make sure that both water flow through the bearing and conduction of heat through the large steel shaft that's running within it is all being taken away. So we don't want to see the temperature of the bearing increasing with time, because that's telling us that something is overloaded or a water cooling system, we have not enough water coming to it. We really need to keep the bearing temperature controlled so that we don't have overheating of the bearing material, which is very similar to the situation with an oil and Babbitt bearing. You have to monitor the temperature to make sure that you're within the design limits of that bearing. So one of the things Ryan and I have both talked about before with people, and I think we've even presented on it in the past, is this difference sort of in the evolution of water lubricated bearings. The earliest ones, of course, people that are familiar with wood bearings, we've got strips of wood that were typically put into the housing as staves. And that was the way to make a water lubricated bearing before there was any other material advancements. And so the wooden staves were fitted between wedge blocks or, different ways to secure them into that housing. And as we started using modern polymer and composite materials for bearings, we have the ability to make them as full sort of half shell bearings, as split bearings, which means we can get a lot more load carrying area in the bearing. We don't have to have these big gaps between the staves, and having more bearing area increases the load capacity. It also helps to increase the water film effect, building up the water film thickness. So you can kind of see these two diagrams are just showing the pressure profile that's created by that rotating shaft. And so each one of these pressure profiles is representing the ability of that bearing to lift the shaft or to support that shaft. And so the area of those pressure curves is kind of how much load you can carry. So you can see in this full form bearing, we can get a much bigger load carrying area and spread that load over a bigger part of the bearing. The other big advantage is that when we only have to fit two pieces, we have more possibilities how we can fit that into the housing in place with the bearing housing remaining. And it's easier for fitting the split shell than a whole bunch of individual staves. So I just wanted to touch on the importance of water flow. Just like in an oil bearing, the oil is, the lifeblood of the bearing. Same thing in a water lubricated bearing. Having good water flow to the bearing is critical to the long life and survival of that bearing. The water that's being supplied is providing three main functions. One is flooding the space so that you can develop that hydrodynamic film between the shaft and the bearing surface. Two is to remove heat generated by friction. So when you do have that high-speed rotating shaft within the bearing, there is friction being created between the two surfaces and within the water film, and we have to take that heat away so that we don't slowly increase the temperature of the bearing. And the third big one is to flush out abrasive particles. So if you're getting sand and grit and whatever from the river water that's trying to come up into the bearing, we want to be putting a cleaner conditioned water to the top of the bearing and flushing that down through so that we're preventing as much as possible the dirt and abrasives from coming back up into the water bearing. For us, sometimes, well, basically the direction of flow is not that important as long as the flow is consistent and it's moving. So sometimes we get asked, could we supply to the bottom and have it come out the top, or could we supply to the middle? The main thing is that you want to go from an area of clean to an area of dirty. So you want to move the clean water through so that it's acting like a barrier to keep the dirty water from coming in. We have some rules of thumb which we use to estimate water flow. Basically, depending if you like metric or imperial, 0.3 liters per minute per millimeter of shaft, or 2 GPM per inch of shaft as kind of a rough guideline to figure out how much water you should put through a water lubricated guide bearing. We can do a more detailed heat calculation if we know the loading in the bearing and the rotating speed of the shaft, and we can make some assumptions on friction coefficient and temperature increase, but the really simple way is just work with the rule of thumb, and we're almost always having plenty of water then in that case. We always recommend putting some kind of an alarm on the flow because it is so critical to the bearing survival. And so having a flow alarm if you drop your flow below the established minimum set point is really important for the monitoring of the unit. So some of the problems that we hear about relating to water lubricated turbine guide bearings and things that we try to help solve. Certainly overheating of the material. If you have usually a loss of water flow, the bearing material may overheat and be damaged. Rapid bearing wear requiring frequent replacement. So this is influenced by material selection of the bearing as well as the quality and quantity of cooling water. And so usually the bearing wear is attributable to either a cooling water problem or a material selection problem or a loading problem potentially. Excessive vibration is sometimes a topic that comes up, and usually the vibration is a symptom of a worn out bearing. So the bearing has worn so much the clearance has increased beyond some acceptable limits. And so now the machine is traveling through that larger clearance, and that shows up as higher vibration. Occasionally we see sort of a poor design if it's the bearing's not sized correctly, or there's not enough stiffness in the supporting structure, or there could be incorrect clearances in the bearing. And also we see things come up like misalignment where especially if you have kind of shifting concrete or concrete growth, that could be shifting the alignment of your machine, and the turbine guide bearing can end up taking a lot more load than it was designed to do because the alignment has been kind of skewed out of whack. So before I move on, I'll just give Ryan a chance if he's got any words of wisdom on guide bearing.
Yeah, so one of the things I often see is this excessive vibration is sometimes tied into poor design in that area where he says inadequate load area, because when he was talking about the hydrodynamic film, the large gaps between bearing segments can mean inefficient hydrodynamic film, which can cause orbiting essentially within the shaft, which gets picked up as vibration. So if you get bearing wear and your shaft was not efficient hydrodynamically, you can get an orbiting effect of the shaft within the bearing clearance. And the bigger that clearance gets, the bigger it appears as vibration. So if you're fully hydrodynamic, like some of those problems just disappear very quickly. That was pretty much all I had.
All right, that's great. Thanks, Ryan.
Yeah.
So I want to make sure we don't run ourselves out of time, but we're going to do another poll question here quickly, and then we'll get into the examples. So how long should a water lubricated turbine bearing last between replacements? And is it 1 year? Is it 5 years? Is it 10 years? Or is it 20 plus years? Or the favorite answer that's not shown on the poll, it depends. We didn't give you that choice though. So just give everybody a second to answer that before we carry on.
So we had about 67% people say 20 plus years, 27% say 10 years, 7% say 5 years. And no one has said 0 years or 1 year. Sorry.
All right, perfect. I would definitely agree. It should last more than 1 year. And definitely,
I voted too.
yeah, basically, there are some conditions that will affect how long a turbine guide bearing lasts. And so it's important that expectations are aligned with reality. If there's no water filtration and there's lots of sandy, dirty water being pumped through the bearing because it's a very rudimentary water system, achieving a 20-year life is probably not realistic. But if you can control the bearing environment and the turbine is working within the design parameters of that bearing, then a 20-year life is absolutely achievable. And so this is really
one thing to define on the 20-year life, though. A 20-year life without adjustment would be what we would refer to as a 20-year life, where I think a lot of people associate with old water bearings that are adjustable, associate a long life with that, where they're actually adjusting a bearing regularly as opposed to running consistently on the same bearing. So just to point that out.
Yeah, that's true. In the case where there's adjustable bearings, although the bearing itself, if it's bearing blocks, which I'll show in a minute, they can continue to be driven in towards the shaft until they're eventually gone, but you're still having to do that sort of intervention to keep making those adjustments. So what we're striving for really with the full form split bearings is trying to get, that full life without having to touch the thing, basically. So control the bearing environment, have a good bearing design within the loads and design capabilities, and trying to get to that 20 years plus without touching it. So I'll just go through some examples. I want to make sure we do leave time for questions, so I'll go through fairly quickly, but certainly we're happy to talk with anybody after the presentation as well about anything specific. So this one is kind of just an update. We were able to get some data from Portage Power from this unit. This is a horizontal unit. The Thordon material is the orange material there. And this one actually has a smooth bottom with grooves on top, which helps in the horizontal application to get a better lifting effect in the bearing. So this was installed by Lidestroy in 2020 and has been running quite well since. And we just got some wear data at the end of 2023. And we only had a 1/4 millimeter of bearing material wear so far in that bearing. So that is looking quite good. And the condition of the bearing is great. The water system is running well. And so that bearing basically was checked and everything is continuing to run and running fine with that one. This is an OPG site, an older one. This is one of those adjustable block style bearings where the original blocks probably were wood many years ago. They were replaced at various points with different materials. The most recent one was this Delecto material, which is a phenolic laminate. And so this is a 13 3/4 inch shaft. And so in 2023, we replaced the Delecto blocks with the Thordon SXL. So in this case, we supplied the rough material to one of the OPG workshops where they actually machined the replacement blocks themselves and then fitted them into the carriers and put them into that unit. So this is just a case where we've directly retrofitted the old Delecto phenolic with new Thordon material just to try to get a bit more performance out of that machine. Same theme of Big Eddy. There's a lot of Big Eddies around the country, but this is with Valet, their High Falls site, the Big Eddy station. So this one was converted from staves in 2006. So this was the original carrier that got sent down to Thordon in 2006 with the stave pockets. Those were machined out at the time. The carrier was cleaned up and it was fitted with the Thordon split bearing with a bronze taper key set. And that went into service in 2006 and wasn't touched again until just last year. And so the work was done last year, doing some overhaul work at that site. And so those bearing shells came out. They look pretty dirty, but the clearances were still reasonably good. And that bearing had been working quite well since 2006. But because the unit was apart doing overhaul work anyway, it just makes sense to put in a new bearing to get another 20 years. So this one had 18 years basically when it was taken out and overall still looked in really great shape. This is a picture.
I'm just going to add, I saw the customer this week, and the clearances they told me are the exact same as it went in 18 years ago. So there's
Well,
that
that's
too.
good. That's a great
So
endorsement.
that's no.
Yeah.
Yeah.
Yeah, this is just showing the new bearing with the bronze key set. So this is the bronze wedge key that drives down and secures those two split halves into that housing, which I think we've talked about probably many previous presentations. So I'll flip it over to Ryan to talk about two more examples, and then we should be wrapping it up.
Yeah, I'll try and be quick here. So this is Halter with Northwestern Energy, which is an American customer. So they're in Montana, but these were upgrades from the original slide bearing, as I'll call it, a Generation 1 water bearing. So basically they were doing a lot of maintenance and a lot of adjustments. And they were upgrading the unit, and so we supplied new fully hydrodynamic housings, to which you see there's an example of that on the right. So this was a complete new assembly with the fully hydrodynamic bearing and a tapered key set. So the first unit installed in 2022, and considering they were going from a Generation 1 to a Generation 2, they immediately called concerned that the shaft wasn't orbiting. Because they had an old style stave bearing that the shaft is orbiting within the clearance the whole time. So then we did the next unit last year, and the remaining 2 units are going to ship in a couple months here as well to get that station complete. But that is just an upgrade from Generation 1 water bearing to Generation 2. And then this is Tobic Narrows, which is another example of that. This is a turbine upgrade where they took them from 10 to 12 with Andritz and New Brunswick Power. So these are a 440 millimeter shaft diameter. We supplied a new guide bearing, new tapered key sets, with tapered key sets, and a radial shaft seal as well. Water filters were also supplied. So the first unit was commissioned last year. Actually, the second one's not being commissioned until this year in the summer. There was some delays on this one due to COVID as well. But this is another example of we went from Generation 1 to Generation 2 because they're getting performance upgrades with the new unit, the new runners. They're able to run tighter clearances because it's not orbiting, and we've sized it accordingly so they don't have large clearances. So we can go on from that, I think, Greg, unless you have any comments.
Nope. Yeah, so basically just to wrap up, I hope most of that information was interesting and useful for everybody. And generally, both Ryan and myself have looked at a lot of different guide bearings, a lot of shaft seals, a lot of wicket gate applications. And so anything that you may have some challenges with and you want to take a look at trying to improve the life and the performance, then don't hesitate to ask us to take a look. We are very accustomed to looking at old, messy drawings, trying to decipher what's in those original drawings, and then trying to give some ideas and feedback on what might be possible for improving or upgrading the equipment. And there's certainly no cost to you to get a second opinion, so absolutely take advantage of that and ask us for input on anything that you're working on, and we're happy to take a look. So with that, we'll move to questions. And
I think we have one now, and I'll say it and maybe I can even answer it, but
Sure.
what is the ideal clearance for hydrodynamic action? And I think those are not the same thing at all, because clearance and hydrodynamic operation are essentially unrelated. Hydrodynamic operation is basically load within the bearing and lubricating medium. So we're making load adequate to make water operate hydrodynamically. So the clearance could be 0, almost essentially. It could be like 1 or 2 millimeters, or it could be a foot, and you could still achieve hydrodynamic operation if loading and everything is correct. So I don't know if that makes sense, but yeah, so it's unrelated, essentially.
Yeah, I wouldn't say it's unrelated entirely, but certainly the biggest driver of hydrodynamic film development is going to be uninterrupted area of the bearing, right? So a large smooth distance between grooves, and also, as Ryan said, the load and then the speed. Clearance has some impact. If you had a really huge clearance, then you're actually getting more kind of almost a line contact between your shaft and your bearing. So you want the clearance of the bearing to be as small as practical. But that's also driven by shaft diameter, by manufacturing tolerances, by the thermal expansion allowance in the material. So there's a lot that has to be considered in coming up with the optimal clearance in a bearing. So it's not unrelated, but certainly the biggest factors influencing the hydrodynamic film are load and speed and viscosity of the fluid. And the other part there's a second part to that question, I guess, which is about filtering. Is filtering a prerequisite, or can we operate on run-of-river? Absolutely, the bearings can work on run-of-river water. It depends, as I was saying, sort of on the expectation for life and the quality of the water in the river. So if you can maintain a reasonably clean bearing environment with straight river water, then absolutely the bearing can work in that way. It doesn't need to have a 10 micron filtration or something like this. But the more sand and abrasives you can take out of the water that's being supplied to the bearing, the longer the bearing will last, no matter what the material is. Any bearing material will survive better in a clean environment than a dirty one. And so it becomes a little bit of a cost and complexity exercise. Is it worth it to spend the money on filtration systems and getting the water cleaner to the bearing based on how much this turbine makes? How big is this turbine? How much is it worth investing in as well? So I think a lot of old, smaller units will just use straight run-of-river water for sure. And as you get into bigger, newer machines that are being constructed and working with OEMs, it's much more common to have a filtration system in place.
And there's material selections that can be trade-offs and such. So we do have run-of-the-river units running for 25 or 30 years as well with no filtration, but at the same time, as Greg said, it's all down to expectations and what you're working with. And then we have, is PFSA and plastic shredding a concern? I don't believe that is that is completely unrelated. That is not a factor in the material that we are supplying. So that is not present in the SXL material. Water quality requirement is the same as shaft seal as bearing. Yes, so our recommendation, if you want to make a bearing last forever, 100 microns filtration will help you achieve that. We have the same recommendation for our shaft seal as we do for our guide bearing assembly.
Yeah, I think that certainly having cleaner water to a shaft seal is helpful, just as it is with the guide bearing. The difference is that the bearing is seeing a lot more water going through it. It's also seeing a lot more load on it, and so it becomes more important for the guide bearing perhaps than the shaft seal. In the shaft seal, the water is mostly acting like a clean barrier to keep abrasives from coming back in, right? It's providing some cooling effect, but really it's trying to create a clean water barrier space in the seal assembly, which is a little different than in the guide bearing. But in an ideal world, certainly having conditioned water is helpful to both bearings and seals. Yeah, I think we're just about done. So, we've got one more question.
Up to 100. Yeah, up to 100 microns is acceptable for SXL material, but any limitations in terms of parts per million? That sounds like one for you, Greg.
Yeah, the parts per million in terms of water quality it's a hard thing to just say a single number, because it also depends somewhat on the type of particles that are in the water. So smooth round things don't do as much damage to things as sharp particles. So we don't really define a ppm value as a target, but the idea is take out the biggest abrasive stuff as much as we can. So usually we're not defining a ppm number as much as a particle size.
Our filtration skids are going to pull by specific gravity as well. So it's approximately filtering to 100 microns, but it's a gravity or particle weight that's really going to be the filtration method in what the systems that are provided by Thordon, the cyclonic separator style.
All right, I don't see any more questions right now. So what we're going to do is just wrap up the webinar. Thank you again, everyone, for joining us today. If you are interested in hosting your own webinar with OWA, please email me. Jan is going to put my email in the chat there, so please feel free to reach out. I would also like to just plug our conference. So a reminder that the Power of Water Canada conference is taking place May 8th to 10th in Niagara Falls. We hope to see you all there. If you already, please do so using the link that my colleague Jane is going to put in the chat. We also do have some young professional passes available, so please reach out about that deal if you are interested in, additionally to yourself, bringing a young professional with you. That is anyone who is under 5 years in the industry working with you. All right, so thank you again. That was wonderful and informative. I'm sure I speak for everyone here. And thank you to all who joined us today. I hope everyone has a wonderful weekend, and we will see you in the next webinar.
Thanks, everyone.